Hi, in this video, I'm going to go through the AQA AS chemistry paper. This is paper 2 from 2020. I'll just do the first half of the paper in this video and finish it off in a later one. Okay, so, right, first question about chloropropane. Define the term standard enthalpy of formation. Well, that is the enthalpy change when 1 mole of substance is formed from the elements in the standard state. Okay, right. So now here is a question I'm going to use. It's going to use Hess's law. So we've got the equation for this reaction. We've got an alcohol here reacting with PCl3 to make a haloalkane. Right, and they give us the enthalpy change of this reaction, minus 114, and they give us here in the table all of the standard enthalpy of formations, except they don't give it for propan-1-ol, and we've got to use that information to calculate the value for propan-1-ol. So obviously we're going to use a Hess's law cycle here, which I've drawn out here. Right. So this is so I draw an arrow here, an arrow there. Now, which way am I going to put the arrow? Now, when you form a substance, you're forming it from the elements in the standard state, so the arrow should be going up, and the arrow should be going up there as well. Right, let's put in the values then. But on the green arrow, we are forming 3 moles of the haloalkane. So that's going to be 3 times minus 130 for that. This value there. And we form 1 mole of, I've lost an 3 there, of H3PO3, which is that value there, minus 972. So if I add all that up together, we get minus 1362 kilojoules there. Okay, now we know the value on this arrow is minus 144 because they tell us that's the enthalpy change of the reaction. And let's look for the red arrow. Well, we're forming 3 moles of the alcohol there. So we don't know what the value of the alcohol delta HF is. We've got to find that out. So let's call that X. So it's going to be 3X there. And we also form 1 mole of PCl3, which is minus 339, sorry. Right. Now we're going to fill in the Hess's law cycle. Okay, so we know that this green arrow, that's the quick way of doing it. All right, starting there. But you can also do the long way round. It should be the same enthalpy change up there and that way. Okay, so let's put that into an algebra equation. So we're going to get there. Green minus 1362 has got to be equal to the red, which is 3x minus 339. Okay, so we just simplify 339 and then minus 144 there as well. So if we simplify that, we get 3x is equal to minus 909. And so x is divided by 3 is minus 303. Now x is equal to the enthalpy of formation of the propan-1-ol. So that's equal to minus 303 kilojoules per mole. Okay. Now we move on to this question here. It is right, it says chloropropane can also be produced by the reaction between propane and chlorine in the presence of UV light. Of course, this is going to be free radical substitution we're talking about here. And you need UV light for that. Or why do you need UV light? Well, actually, in the initiation state, you need UV light to break the chlorine-chlorine bond in Cl2. And that's to generate the free radicals. Okay. Now we've got to talk about the propagation step. Okay. So there's two propagation steps. What happens there? Well, okay. So we're going to get the haloalkane. Sorry, the alkane, propane, and that's going to react with the chlorine free radical on the right. The chlorine free radical is going to take a hydrogen with its electron away from that, so that's going to form HCl. That's not a free radical anymore. The electrons are paired up in the bond between the hydrogen and the chlorine there. One electron from the chlorine, one for the hydrogen, but that of course is going to leave the alkane behind as a free radical because it's lost a hydrogen with its an electron, so the carbon has an unpaired electron. So we've got that's a free radical. And then in the next propagation step, that free radical is going to react with a chlorine molecule. Right, and that is going to take, right, it's going to, so if you think of our chlorine molecule like that, it's going to take that, and that of course is going to leave this bit behind as a chlorine free radical. So we form a chloroalkane, and we have the chlorine free radical regenerated. So you can see the chlorine free radical doesn't get used up, and this can cycle over hundreds, if not thousands of times. Okay, that's the 3 marks there. Okay, the carbon-chlorine bond in 1-chloropropane is polar because carbon and chlorine have different electronegativities. Right, define the term electronegativity. Well, it is the ability of an atom to attract electrons towards itself in a covalent bond. Don't forget the in a covalent bond bit at the end there. Okay, right. Ammonia reacts with 1-chloropropane to form propylamine. Name and outline the mechanism of the reaction. Well, the name of the reaction is nucleophilic substitution. That's 1 mark out of the 5. Okay, let's draw the mechanism now. So 1-chloropropane. Right. So I will draw this out, this last carbon out displayed to make it clear what's going on. Right, so there's, here is our ammonia. And ammonia has got a lone, the nitrogen's got a lone pair. Now, you don't have to put that on, but just there's a delta partial positive charge on that carbon. The pair of electrons, the lone pair goes to the carbon. Okay, and then the carbon-chlorine bond is going to break. So we draw the arrow from the bond onto the chlorine. Right, and that is going to give us, let's do it at the side actually. So that'll give you another 2 marks for each of those curly arrows. And that will give the intermediate. The nitrogen is now forming 4 bonds. Now we have the chlorine has come off as a chloride ion. Okay, so the nitrogen has got a positive charge on it. That is usually the case when nitrogen is forming 4 bonds. Okay, it will have a positive charge on it. The final step in the mechanism then is for that nitrogen to lose one of the hydrogens, and it's acceptable to just show it like this. So you just show that bond breaking, so the pair of electrons go back into the nitrogen from the lone pair there, and we'll form the product. product is going to be propylamine. Nitrogen, no positive charge in it, just 2 hydrogens on it now. Okay, now you can, and then the hydrogen will come off as H+. Now it's perfectly acceptable to show it that way, and you'll get full marks for it. But of course, H+ doesn't really exist by itself if it gets picked up by another ammonia molecule. So the bit in green I'm drawing, you don't have to draw it to get all the marks. But just you've probably seen it written down like that. So that picks up that hydrogen there, and then that's going to form the NH4+ ion. So I suppose that is a more correct way of showing it, but you don't have to do that in order to get all the marks. There's your ammonium ion there produced. Okay, number 2 then. It's about rates of reaction, and this is actually required practical 3, I think. That's why they're asking about it. Right, so the effect of temperature on the rate of reaction between sodium thiosulfate, which is that, and dilute hydrochloric acid. Okay, so when they react, they produce sodium chloride, sulfur dioxide, and hydrogen. It also produces solid sulfur. That makes that will make the solution appear cloudy, and you measure how long the reaction takes by measuring how long it takes. You put the flask on a cross, and you look down on it, and you measure how long it takes, so that you can't see so that it becomes so cloudy that you can't see the cross. That's what they're doing in this experiment, and here are the results of that experiment. So they've done different temperatures, measured the time taken to disappear, and then here you see this familiar thing where they put 1 over the time taken. This is proportional to the rate. The rate of reaction is proportional to 1 over the time taken, so that's how they're calculating rate there. Okay, let's do the questions on it asks then. So the student uses a stopwatch to measure the time. The stopwatch shows each time to the nearest 0.01, but why does it the student only record it to the nearest second? Well, that is because a person's reaction time, you can't realistically justify it measuring it, certainly not to 100th of a second or even a 10th of a second. 1 second is the closest you can say, really. Okay, the rate of reaction is proportional to 1 over T, as I said before. So we've got a complete table 2. So we've got to fill in that square there. So all we've got to do is 1 over the time, which is 12. The 1 over 12 is 0.0833 recurring. So we'll do it to the right number of decimal places, the right number of significant figures, sorry. Like the same, they're all given to 3, so I've given it to 3 as well. Okay, so now they've asked you to plot a graph where you have plotted rate of reaction on the x-axis here against the temperature, no, the y-axis even, and the rate, and this is the temperature on the bottom. Right, if you plot those, I've plotted those, all of the points there. You can see the one I've circled in green is definitely an anomalous result, so ignore that. And the others are pretty clearly on a curve, not a straight line. So if you drew a straight line, you'd lose a mark. You should be drawing a curve of best fit like I've drawn there. If you just look at the results as well, you can see that that one, the anomalous one, this one here at 44 seconds, it's clearly wrong. Well, something funny going on there because it goes from like 26, should be going down, it goes up to 44. So that's it's going to be not quite right there. Okay, use your line of best fit to estimate the time for the cross to disappear at 40 degrees C. So we're going to have to interpolate using the graph. So I'm going to draw a line up from 40 degrees C there and across there. Right, I think that is about the rate there is equal to 0.033. So the time taken is going to be 1 over there, 1 over 0.0033, which is 30.3 seconds. Okay. I'll just do to the nearest second. 30 seconds. Okay. Right, now, suggest by considering the products of this reaction, why small amounts of reactants are used in this experiment. Now, this is one of these questions where it's not always 100% clear what they're trying to get at. But it does say small amount. Why small amounts? And consider the products. Right, let's look at the products. What have we got? Right, we've got sodium chloride. Nothing wrong with that. Sulfur, fine, hydrogen, water. But we have got sulfur dioxide, which is a poisonous gas. So that's why you want to limit that's toxic. So you don't want to make too much of it. That's the answer they're looking for there. And you may remember when you do this experiment, that's why it's probably quite important to do the required practicals. It helps you remember things. When you do this experiment, when you finish with it, you've got to put it in you've got to throw the waste into an alkaline waste bucket, not put it down the sink because it's making SO2. Okay. When the alkali will stop the SO2 production. Right, the student could not do the experiment at lower temperatures, could do the experiment at lower temperatures, but the student chose not to carry them out. Why not? Because they would probably take too long. Right, now, this question is about organic synthesis. 2 ways of making methyl propanol, and I think they're going to get us to think about percentage yield and also about atom economy. Okay, so if we look, right, so in each method, the student uses 1 gram of the organic starting material. Give us this table over on the right here. Right, calculate the percentage yield from method 1. This is what we're going to do first of all. Okay, so the percentage yield from method 1. Right, now, so we can see that. So what mass do we actually make? We make 552 milligrams. So the mass made, the actual mass product, 552 milligrams. Let's convert that to grams. That's 0.552 grams. Now let's work out when you're working out percentage mass, you need to work out the theoretical maximum. That's what we're going to work out there. Okay, so it did tell us we started off with 1 gram of reactant. So we need to work out the moles of reactant. That is butanoic acid with a methyl group and a ketone group on it as well. So anyway, the moles of reactant, mass over MR. Well, we're starting off with 1 gram, and the MR is 116. That gives us 8.62 times 10 to the minus 3 moles. Right, now we need to work out, well, we say if we've got 1 mole of the reactant, that reacts to give us 1 mole of product. So let's do moles of product. It's going to be the same. So you're going to get 8.62 times 10 to the minus 3. So let's do the mass of the product. It's going to be moles times the MR. So 8.62 times 10 to the minus 3 multiplied by the MR, which is 72 of the product. And that gives us a theoretical maximum mass of 0.621 grams. Okay, now we need to do the percentage yield. Running out of space a bit, but percentage yield, well, that's going to be the actual mass, which is 0.552 grams, divided by the theoretical mass, 0.621, multiplied by 100, That gives us a value of 88.9%. Right, next part. Right, now we have got to calculate the percentage atom economy for method 2. Okay, so I'll try and just move this down here. So there's method 2, that's what we're interested in. Right, so what is atom economy? Atom economy is equal to the mass of the useful product over the total mass of product multiplied by 100. Right, now when we make, let's have a look at the equation here for method 2. We make, let's see there, we make one, every time we make 1 mole of product, we also make 2 moles of water, which is not useful, okay? Right, what is the mass of 1 mole of product? Well, we're going to do mass is equal to moles times MR. We make 1 mole, so that's times 72, that's the MR of that, 72 grams. Right, let's work out the mass of water we produce. So mass is equal to moles times MR here. So we've got 2 moles of water, and the MR of water is 18, so that's going to be 36 grams. So let's put these two numbers into our atom economy equation in green on the left there. So the mass of the useful product is 72 grams. The total product is going to be 72 plus 36, all times by 100. You do that, you get an atom economy of 66.7%. Okay, so there's that bit. Now, I have actually not pasted in the question here, but it says, what's the importance of yield and what's the importance of atom economy? So I'll just explain that now. So why do you want yield? Why do you want a high yield? So you can use less starting material. Higher the yield, the less starting material you'll need to make a certain amount. And the atom economy, why do you want a high atom economy? So you make less product, waste product. So now in this example here, it's not really that relevant. I wouldn't have thought, because you're only making water. That's not not really difficult to dispose of. But anyway, that is why you want a low atom economy, a high atom economy, sorry. Okay, question about Pentane 2-ol and Pent-1-ene. So the boiling point of Pentane 2-ol is pretty high, much higher than that of Pent-1-ene. And explain why it's high. Right, of course it is because Pentane 2-ol, they can form H bonds, which is the strongest intermolecular force. And you need a lot of energy to break that. A lot of energy to overcome them. Whereas in Pent-2-ene, Pent-1-ene, sorry, it's not all of those, it hasn't got a dipole moment. It's only made up of carbons and hydrogens, which have equal electronegativity. And there's no possibility of hydrogen bonds, so the only kind of forces you're going to get are van der Waals forces, molecular forces, and they are weaker. It's only 3 marks. You don't have to go on about explaining how a hydrogen bond forms. That will be sufficient. Okay, Pent-1-ene is formed by the elimination of water from Pentane 2-ol. State the reagent and conditions of this reaction and outline a mechanism. Right, so the reagent you need is concentrated either phosphoric acid or sulfuric acid. I'll put sulfuric acid. Again, this is a required practical, and this is required practical 5A. And The conditions you need for that, you need a high temperature. I think it's sufficient just to say high temperature without stick. Now the outline, the reaction mechanism. Okay, so right, so we're going to have what is it, pentane 1-ol, pentane 2-ol, sorry. Right, I think I will do it this way around 1 minute. I'll draw this end of the molecule displayed. It's pentane 2-ol. And here we're going to, I'll just write that as CH2, CH2, CH3. Okay, now the first thing is that you protonate the oxygen there. So you have an H plus, and really, if you're going to be really correct, like in the last one, you should really write down that as show that's part of the sulfuric acid, but there's no need to. If you look at the mark scheme, you don't need to do that. So you should show. I'm just going to put that goes onto there. But if you were doing it in green, if you were being really correct about that, you should probably draw that going onto there, and then that going onto the oxygen. Okay. As I say, it's just perfectly acceptable to draw it like that. So I'll get rid of this. Okay, so you're going to protonate that now. So we end up with now we've now got a positive charge on the oxygen. The rest of the molecule remains unchanged. Okay, now the next step is for the water molecule to leave. So we're going to draw that. So that pair of electrons in that bond is going to go onto the oxygen. And that is going to leave us with a carbocation behind. Okay. And now the final step there is for that pair of electrons is to go onto there to form the pi bond. And to form pent2-ene as the product, pent1-ene as the product. Right, that is our mechanism. Right. I did say pent1-ene, didn't it? Pent1-ene. Yeah, I thought it said pent2-ene for 1 minute. I thought I'd have to do that the whole thing again. It did say pent1-ene. Right. There is an alternative there. If you want to, you can have like these last two stages happening in one go. So that's stage 1. So we call that stage 2 and stage 3. You can have them happening in one go, and you don't show the formation of the carbocation. But I've decided to do it that way. You get full marks for either way. Right. Now, big, long, descriptive question. Question 6. This is the introduction to organic chemistry bit of the spec, section 3.1. Explain the differences between structural isomerism and stereoisomerism. Okay, right. I think we need to give a definition of structural and stereoisomerism. So structural isomerism. So the molecules are the same molecular formula. But different structural formula. Okay. Whereas stereoisomerism, I'll probably come back to this later, but I'll put it in now. Stereoisomerism you need to say it's got the same structural formula, same molecular and structural formula, but different arrangement of groups in space or atoms. Okay, so you've got your two definitions down there, which you really should put in. Okay, but now we've got to use the examples to illustrate that. And we've got to show the three different types of structural isomerism. Okay, so now I'm going to leave stereoisomerism alone for a minute, and I'm going to just talk about the structural isomerism bit. Right, there are three different types of structural isomerism. Right, we can have then, I'm going to use C4H8 to illustrate this. We can have functional group isomerism. That's when the molecules they've got the same molecules have got the same molecular form. They've actually got different functional groups. Now here we've got C4H8, which means it can either have a double bond. If you look at the carbon hydrogen ratio, there is NCNH2N. So it's either got a double bond in it or it's a cyclic molecule. So an example of two functional group isomers would be, let's say we have but1ene, so I'm going to just draw them. Save time, and I'm going to draw them as CH2CH3. And a good, right, so, and you can have cyclobutane. Okay, two hydrogens on each, right, CH2 and all of those, yeah. Be two hydrogens on each carbon. Okay, so they're functional group. Same. All right, now let's do the next thing, which would be positional isomers. This is where they have the same functional group and the same kind of carbon skeleton, but the functional group is in a different place. And a good example of that would be if you had but1ene here, where it's between 1 and 2, and but2ene. I'll draw that like this. But2ene. Do that CH2CH3. So that's but1ene and but2ene, or right. The final kind of structural isomerism is chain isomerism. That's where you've got chain isomerism. You've got the same functional group, but the carbon chain is different. So, for example, we could have but1ene again. Let's have that. So you've got in the carbon chain, you've got 4 carbons in a row. And let's have methyl propene. Okay. So this one here, it's got the same functional group. They've both got an alkene functional group, but you've got a different carbon skeleton. If you like, the one on the right is branched, the one on the left is straight. Right, that just leaves us now to talk about the kind of stereoisomerism, which we can talk about here with these molecules. And of course, that stereoisomerism kind is geometric isomerism. So it's geometric. There's another kind of stereoisomerism, which you do in year 13, called optical isomerism, but this is an AS paper, so that's all we need to talk about here is stereoisomerism. is it geometric? And that's when you have a double bond. And remember with it, and why do we get this? Is because there's no, if you need a double carbon-carbon double bond, and you don't get no rotation across the double bond, and that gives rise to two possible stereoisomers. Okay, so I'm going to draw butene, which is the only thing with C4H8. The only C4H8 molecule that can show this is actually butene. Butanene doesn't. There's a double bond between the carbons there, and all of these bond angles will be they'll be 120 degrees. Okay, now I'm going to draw them looking like they're 120 degrees. Now in butene, you can have the hydrogens on the same side as each other, the methyl groups on the same side, and you would call that together, so that's the Z isomer. It doesn't say isomer. Or what you can do is you can swap these two around, and you will form the E isomer, and these two forms can't interconvert because you'd have to break the double bond, and that of course requires energy, so that doesn't happen. So you get two distinct forms, two stereoisomers. You get the E, and this one here, it's the E isomer. Okay, and all of that should give you 6 marks, and that's quite a long 6 mark. It would probably take longer than 6 minutes to write it, which is unusual. Okay, right, let's now, right, I think this question is about polychloroethylene. Okay, give an equation showing the structural formulas for the conversion of chloroethylene into polychloroethylene. Okay, so let's do that. So we're going to have chloroethylene, and so I'm going to draw this. This chloroethylene, and what's going to happen is you're going to get a load of chloroethylenes. I'll draw one next to it. You wouldn't put this in your answer. I'm just going to draw it. You're going to get thousands of these, yeah. And what is going to happen is you are going to break the double bond here, and then you're going to form a new single bond to the neighboring. Yeah, that's how it forms to form this long chain. Okay, so I'm going to, that's just to show you, I'm not going to leave that in my answer. You shouldn't leave that in your answer. Now, to show there's lots of these, you should put an N in front of it. So N molecules of chloroethylene, and in the product, the way to draw it is, of course, you only draw one repeating unit. Okay, and you want these bonds, okay, and then you want to put a square bracket around that. That is the repeating unit within the blue square brackets, and we put N there to show the polymer. Okay. Now, the next question, I think it asks, does this product react with bromine water? Right, what would happen? It doesn't react with bromine water because the product, the polychloroethylene, doesn't contain any double bonds, even though it sounds like from its name, it's got E in its name, it doesn't actually contain any double bonds. So add bromine water to that, nothing would happen. It would remain red. Right, now plasticizers are often added during the manufacture of PVC. The structure of the plasticizer is shown below. We're going to deduce the molecular formula of it. Okay, and let's do that first of all, and then we've got to say why you add the plasticizer to PVC. Right, let's do a quick way of doing the molecular formula. So what I'm going to do is I'm going to count up the carbon atoms first. So I've got 1, 2, 3, 4, 5, 6, 7. Well, I've missed one out there. There's 8. So we've got 8 carbons there. Now look, this bit here is exactly the same. So I'm going to do, let's put 2 times 8 carbon atoms. And I've also got, in addition to that, so that's 16, and I've got 17, 18, 19, 20, 21, 22, 23, 24. So it's C24. Okay. Now, rather than work out the number of hydrogens, there's a sort of quick way of doing that. C24, if you only have carbons, hydrogens, and oxygens in the structure, it doesn't work if you've got nitrogen in it, so don't use it then. But what you can do is this, you can say, right, if there was no double bonds and no cyclic things in it at all, it would be CnH2n plus 2. So that would make it H48, H50. Okay, now every time you have a double bond or a ring, you subtract 2 hydrogens. Okay, so how many double bonds have we got here? We have got 1, 2, 3, 4, 5, plus a ring. That makes, so that's going to be 6 lots of 2 hydrogens, which is equal to 12. So we've got to subtract 12 from that 50 there to get our answer. And then we've got to add on, don't forget we've actually got 4 oxygens as well. So the answer is going to be C24, 50 minus 12, which is 38. And we've got 4 oxygens, put them there. Okay, so that's nearly halfway. But we just say, why do we add a plasticizer? Right, you add a plasticizer to disrupt the van der Waals forces between the polymer molecules to make it more flexible. Okay, so they get between the polymer molecules, reduce the size of the van der Waals forces by reducing the number of points of contact, which makes the thing more flexible. Okay, it's halfway, so I will leave that there.